Hello to all of you. We have heard a lot of stuff so far. Now I really try to go a step deeper into a scientific point of view. I think if we want to have that our discipline goes from a handicraft to an engineering discipline, we need science. So I will give you a kind of an approach which allows you to have a very scientific understanding of architecture and all the practical issues of architecture which could be backed up by such a scientific approach. Maybe before I go into the technology, let me just mention something which I think is very important. I'm in the field now for about nearly 40 years. And when I started to program, I programmed at the Munich computer Perm. If you want to look at it, go to the Deutsche Museum. There you find it. And I've seen all the developments since then. And I think no one, really no one of us, had an idea that our discipline would develop in such a way as it developed. And nowadays, everybody has a computer in his pockets. Everyday life is done by using computers and actually by using software. So we are now a discipline which we were not 30 years ago, which is the most important discipline in the field. And I have the feeling a lot of my colleagues didn't understand that so far. This is also why I took over this not so easy position to be the founding president of the Center Digitization in Bavaria, because I think what we see now, digitization, digital transformation, is the largest change due to technology in the modern era. It's certainly more change than by the automobile, and it's perhaps more change than by the invention of Gutenberg book printing. And what comes with it, it goes with a speed which is a higher speed than we have ever seen before. And this is a saying by Mark Anderson, who's an entrepreneur in Silicon Valley, he has done Mosaic, one of the first widely used web browser, and he has a very nice article. If you want to read it, just Google it. It's very simple. Software is eating the world. Sounds a bit strange in the beginning, but if you look a little more carefully, you find out why he's saying that. Because we will see that everything, literally everything, will be dealt with software. And it has also related to something which I found remarkable. When I started to program, programs were running on batch machines, and they were completely separate from the physical reality. And nowadays, nearly every software system is directly connected with reality. So we go from standalone software to cyber-physical systems, and that makes a big difference. And so we have to deal with software in the digital age, and software is the main factor to create innovative products, innovative processes, instruments to reach the customer. Bertrand mentioned that I do a lot of work with the automotive industry, and I've seen also development there. And we will see that software is becoming the most important discipline in the automotive field. By the way, not everybody in the domain of automotive engineering has realized that. But even today it's true and will become more true in the future. And as a consequence, and this is another issue, it's not just the cars, it's the whole processes in the companies which change completely. So automotive companies have to become platform companies. They have to understand what it means to do software with time to market, and they have to understand software evolution. We have not heard a lot about software evolution today. I think this is one of the big challenges in software engineering. The software is longer lasting than ever other technology. Nobody of you would use a computer which is 30 years old. But if you look inside the computers, you find software which is 30 years old. And so we have to take care of that. And now let's look at the crucial aspects of software engineering. I can be short about that because we have heard about that already. Its requirements, its architecture, its quality, its evolution. I happen to look at projects from time to time. much too often at projects that are in trouble. And even without looking at the project, I know where the problems are. Its requirements, its architecture, its code quality, and its evolution. And it's surprising because we understand now much better how to do that, but it's a long way to go from understanding it to bring it into practice. And I will talk about architecture today. I think architecture is key. And if I talk about architecture, I'm not just talking about the classical idea of software architecture, which is also sometimes called fine design or architecture in the small. I think we need architecture which is good both for systems and for software. And a lot of the things we are dealing with are cyber-physical systems, and we should have a notion of architecture which addresses both. And architecture for me is structuring of large systems, and we have large systems, into elements. And there are two basic tasks of structuring the functionality and structuring the system into components. There is not too much work on structuring the functionality. I call it functional architecture or functional feature architecture. If you look into a car and you count how many functions are there that are based on software, we have counted that, and that's already 4 years ago. We come up to 4,000. And today there are even some more. And therefore you need a structured view on those functions. Today some of the speakers was talking about the relationship between the features. This is another important thing. We have studied a lot of software in the cars, and in the software in the cars you have a lot of feature interactions between the functions. There are nice feature interactions. If you listen to your telephone, to a radio and the telephone call comes in, then it's of course fine if the radio is turned down. But there are hundreds of feature interactions in cars which are not liking. And I can tell you a lot of stories, war stories, how things went wrong according to those feature interactions. So I believe one level of architecture is functional architecture. And since you talked about use cases, I think use cases is a very interesting technique to support functional architectures. And then you have solutions. So you have to decompose a system into subsystems, and this forms an architecture. In both cases, you have to understand how these different elements interact. And so you need a notion of interacting elements there, and you can consider that at a level of being platform independent or platform dependent. I will today only talk about platform independent approaches, but it is possible to transfer this work also at a level where you talk about platform dependencies. Another question is, how well is our methodology today to design and specify architectures? And I will give you a theory of specifying architectures. And I'm not saying that I recommend to use that theory in the sense of formal methods. There's a lot of work in formal methods which is not formal and which is not methods. I'm interested in a scientific foundation. And this is important because if you want to justify methods, you call it practices, then I need a scientific basis which tells me which are the steps which I can go and be sure that they lead to correct software. So if you look at architecture, what are the key elements there? And one of those key elements are interfaces. Interfaces are the way to connect subsystems to each other. And if you ask the question, what are the functions of a system, of a car, of a smartphone, these are also behaviors that are described via interfaces. And if I say interfaces, I'm talking about interface behavior too. I do not talk just about what you see sometimes in object orientation, that they give just syntactic interfaces. That is not enough, that's quite clear. So an architecture is determined by the set of its elements, the structure of its connections, and the data flow between these elements. You could distinguish static architectures or dynamic architectures. I will, for simplicity, just talk about static architecture during my presentation, but what I present here could be extended, and we did that to dynamic architectures too. And as I said, I consider, if I look at a system, I consider two architectural views. One view is the functional architecture, which describes what are the functions that are offered by the system in a structured way. And so you are interested to understand that and their functional dependencies. And then we talk about the subsystem architecture, and I'm just talking about the platform-independent part of that, but you can also go to the platform-dependent part. And if you want to understand an architecture, you have to understand the role. We have heard about blockchain today, and blockchain is an interesting example of an architecture, because if you implement a blockchain system, you have to implement an architecture. And then you have to describe the roles of the components and their properties and how they are related by interfaces if you do the design in detail. Before I go into concrete descriptions of architecture, I just wanted to mention that, of course, you can also think about architecture meta-models, which means that now you talk about architectural types, types of syntax, types of semantic interfaces, types of composition. You can talk about hierarchical architecture. So there's a lot to do there. You can talk about architectural styles and patterns. So if you want to describe patterns, architectural patterns or design patterns, of course you need, again, a concept of describing architectures. But I will just talk about architectures as such, and what is the essence. First, I believe that when people talk about architectures, they often talk about concrete systems, and they say, look at the architecture of this system. And we have done a lot of work in looking at existing systems. And the funny thing is, if you get a large piece of code and you look at it, you don't see the architecture. You need an additional description of the architecture. And so therefore, I believe architecture design means to design the rules and the structures and the roles that you want to have, and an implementation has to follow that specification. So architecture design is specification of architectures and not implementation of architecture. And then you can ask whether you when you look at the implemented systems, you can ask whether the implementation is correct with an architectural specification. And so we get a universal concept of architecture, and we need that, where we talk about services in terms of interfaces, services in terms of interfaces for sub-services, for subsystems, and now it gets interesting because we need concepts of architectures that allow us to talk about time. Most of the programming languages are not able to talk about time, which is a disaster in a situation where we have to talk about cyber-physical systems. Most of the architectures that are around do not follow the idea of concurrency and parallelism. We need architectures where functions or components exist in parallel, are concurrent, and are distributed. And if you look at that, you realize that most of the programming languages we have till today are still von Neumann languages. Although the object-oriented languages are von Neumann languages. So they are inherently sequential. And Bertrand showed you how difficult it is to go from such a sequential von Neumann language into a situation where you talk about parallelism. And that's inherent. And therefore, we have to start from the very beginning in a situation where we don't have the right languages so far, with an architectural concept which supports all these issues of distribution and concurrency. And that has to be modular, and I will go deeper into that. As I said, for me, the key to architectures are interfaces. The behavior of functional features are described by interfaces. The behavior of components are described by interfaces. And these interfaces occur everywhere. So one of the key issues is specifying interfaces. And now let's do that. I introduce now a concept for specifying interfaces which is good enough to describe both services, so a functional feature architecture, and is good enough to describe components. And so we need two things. We need, on one hand, the syntactic interface idea, which I think you all know. And I have now, in addition, to introduce a semantic interface idea. And let's do that. What is an interface? Syntactically, an interface defines what are the principal steps of interaction over the limit of a system. This is exactly what an interface is about. And if you want to talk about the behavior, we have to understand what is the logic between these different steps. And I decided now to define a set of input, data, messages, events, actions, whatever you like, and a set of output, data, messages, event, whatever you like. This is a first very crucial step. Bertrand mentioned, for instance, communicating sequential processes by Tony Hoare. Tony decided to choose an approach where he did not distinguish so clearly between input and output, and he had to pay for that. Today, the systems we are using are basically data flow systems in the end. And data flow systems are input-output oriented systems. Therefore, I decide to go in that direction and to come up with an idea of an interface, and I give you a picture now. The idea of an interface is now given by a set of channels. The X's and Y's here are channels, and channels are input and output channels. Each channel has a data type. The data type explains to you which data can be communicated over that channels, and these communication over those channels is done in a real-time frame, and it is done in parallel. So you can receive on all the channels messages in parallel, or send on all the channels messages in parallel. And this is already the syntactic interface. We worked for a long time to keep the model as simple as possible. So the idea was, and we do that, we teach that model also to engineers in practice. The model has to be simple enough that you can teach it to engineers within one day. And this is possible with this. Now, first step, we have introduced the syntactic interface. Syntactic interface is a set of input channels, a set of output channels, and their data types. We can also now talk about behavior. I would do it in a completely logical style. I would use what I call interaction or interface assertions, which talks about the behaviors of systems. And if we have interfaces, we can also talk about reverse interfaces, and we change the role of input and output. And here you have the basic idea of the semantic model. And to give a semantic model to this interface idea, the key is to give a semantic model to the behavior on channels. What is the behavior on channels? It's basically a data stream, so the old data flow idea. And I use a simple real-time model. You can use a more complicated one, but for discrete systems, this is fine. I use an interface model where I understand time like the natural numbers. If you like, time is divided in a number of intervals, and each interval gets a number. And so I explain what's happening in these intervals in a way that I say each interval gets a sequence of messages which is sent over this channel in this time interval. And that's the whole idea. And having that, I have already introduced a semantic model for systems. And without going into all the details, we can look at the first specification. This is a specification of a behavior of a system, which is a transmission system. And to explain the transmission systems, I use just one logical formula. And of course, I chose a simple system. Also, so simple is it not. You can try to use your best specification technique to describe it. And it's, from a lot of approaches, it's not so easy. And it says you have an input channel. You can also do it in a graphical way. You have an output channels, so you can just indicate that, and you have a specifying interface assertion. And here you see the logical explanation of the specifying interface assertion, and I have to read it for you because I use some notation which I didn't introduce. So I say for all possible messages which I consider, the number of copies of the messages in the first in the input channel is like the number of the copies in the output channel, and that's the specification. And then now I have specified a transmission system. It's just specified by a logical formula. So it's a little bit like transferring the assertion logic of Tony Hoare into systems. If you are interested to talk about timing properties, you can do that. Now, without going into deeper, I can say, well, this is a system which transmits messages. It is guaranteed that every message is transmitted. Every message that is transmitted was sent. So this is classical what we expect. But now we can talk about time. We can talk about delays and deadlines. So we can say it takes a delay of a certain time until the message comes out when it is sent, and is guaranteed that is received after some deadline. So we can talk about time. But now there's another thing which I found most interesting. This means we can also talk about probabilities. That brings an interesting question into the field. Is software something where it's a good way to talk about probability? Has software probabilities anyhow? And I'm not talking about random procedures. And the answer is no, it's not, because software in a certain say, we would expect that this is a logical thing where there is no probabilities in it. But if you use cyber-physical systems, then you talk about the probabilities of input. And if you talk about the probabilities of input, you want to talk about, given a certain distribution for the input, what is the distribution for the output? And therefore, probability is very interesting. And here I said, I want to have a probability that my time requirements are fulfilled, which is more than 80%. It's interesting because if doing so, you get an interface notion with probabilities. That has consequences. If you look at the classical quality aspects of systems, like reliability, which is considered often a lot of people don't like the term non-functional property, it becomes a functional property. In the approach I am presenting, time is a functional property. Also, IEEE standards say it's not. And therefore, if you go in that direction, you have to rethink a number of things which are, at least to the standards, in the first step, defined in a different way. So now we have interfaces with behavior, which can be specified by logics. We can talk about time, and if you like, we can talk about probabilities. That's the idea. So we have a really expressive interface theory that way. And now let's work with it. An important thing is composition. I will show you logical composition given two specifications of two systems, and now I compose them. To keep things simple, I compose it in a way where I say the composing interface is exactly those channels where one system offers the channel as an output channel and the other system takes that channel as an input channel. So we get a simple way of bringing those things together. In my example here, I have just two channels here, one to the right and one to the left, to keep things simple. Now we have those specifications of the systems with their interfaces. Now let's talk about the result. The result is a system which is a composition of these two. We get these channels as the remaining channels, and now the interesting question is, how does the specification of the composed systems look like? And it took us a while to do the theory in a way that what I show you now is true, and that's it. Isn't that a beauty? It means if you put two things together in parallel, with feedback, with interaction, this can be done at the logical level by logical AND. So logical AND mimics parallelism, and channel hiding is done by existential quantification. So we have a logical reflection of what's going on in building the architectures. This is just repeating what I said. So if you have two systems with specifications, you get here what you get for the composite system. What is also interesting is, and I will show you later details, you can also talk about maybe I should go back to this. You can talk about what's going on here. So you can also derive assertions which describe the properties of the connecting channels, which is important. Why is it important? You can introduce watchdogs, for instance. So you have a lot of possibilities to play around with what you got. Now, let's talk about structuring interfaces. Think about a car. Try to describe the behavior of a car by an interface. A car has about 20,000 messages, different types of messages, that go into the car, come out of the car. Let's sit down and write a logical assertion which describes what's going on. No way. No way. In principle, it's possible. But who could do it? Well, the idea is let's structure that. Let's decompose the interface of a car or a smartphone or whatever we have into a number of sub-services. So we specify the telephone and the light system and the automatic window and the braking system in separation, and we put together from this the whole car. To keep it simple, a nice idea would be we have two functions, and now we put them together. Wonderful, everything is fine. Unfortunately, these functions in practice are not independent. They show feature interactions. And now we have to think about how to model feature interactions. And we worked for quite a while. If you look at the result, which is, I consider is very simple, it is amazing that it took us such a while to find the result. So the idea is we introduce additional channels, which we call modes, and which allow the two functions to communicate with each other. And in these communications, they realize feature interactions. So if this is our telephone, the telephone tells the radio, shut down. And later tells the radio, now I'm ready, you can start again. And it works. We have done that. We have worked with companies on that, and they are in the process of using that. And it allows them to give a formal model of their functionality and their feature interaction. So if we have an isolated function and we construct a refinement where we introduce these mode channels and we put them together and we get a composed system. And of course, this can not only be done with two components, it can be done with many. And now we come to an interesting experiment. Think about it. I said in a car we have 4,000 functions. Now it would be possible to specify these 4,000 functions, to specify each function in isolation, to think about the feature interaction channels, and then to compose them, and I use exactly the composition that I've introduced. And I get a full description of the car behavior that way. Now, I know a lot of people don't like to write logical specs, but of course you can do it also in a different way, because we have shown that we can replace each of the logical specs by a state machine. A state machine with input and output, a Mealy machine, or more precisely a Moore machine. And now you can give Moore machines for each of those things, and it's not so difficult. It's not so difficult to write a Moore machine for the light system of a car or for an automatic window. And now we can compose the Moore machines. And by the way, we have proved that the composition of the Moore machines is exactly leading to the same result as the composition that I've shown you. And this means that we can produce a full, let's call it a prototype, of the car functionality that way. And now let's talk about cost. How much does it cost to produce a specification of one function? Let's assume it costs 10,000 euros, which I think is a fair price. If you consider 4,000 functions, you need 40 million euros. Would it be a good idea to spend 40 million euros to have a full functional prototype of the functionality of a car, which you can test, from which you can generate test cases, which you can simulate? Not so bad. This is what I already said, structuring those interfaces so we can go on. Another interesting thing, and now I show you some interesting parts of the architectural and interface theory I'm introducing, you can also talk about assumptions. When you build a system, often you think about input which fulfills certain constraints, which I call assumptions. For instance, in a car, you would assume that if you measure the speed will not change more than, say, 10 kilometers per hour if you are sure that you make the points where you measure the speed close enough. Those constraints are very important if you do design, because your design depends on those constraints. I can give you a number of errors, of mistakes, of failures in practice which have to do with that. And you said, you talked about Ariane 5, right? And in Ariane 5, there was a silent assumption which was true for Ariane 4, but not for Ariane 5. If they had written down the assumption explicitly, they had known. Now you can do those assumptions. An assumption is nothing as a specification of the inverse interface, which is a specification of the context in which a system is used. And I give you an example. Let's take the transmission component. I introduced now a simple assumption. The simple assumption is, now we have a difficult transmission system. We don't know how long it takes, but it has a property that it can only carry one message at a time. So you are only allowed to send the next message after the message was delivered. This is exactly what I wrote in this assumption. And only under this assumption you get the commitment, which is a specification of the system. So an assumption is a specification like the others. And when we want to have a specification which is not just talking about assumption, but talking about the logics, it's simple because we just transfer it into an implication. And here we have the system specification. We have used that assumption, where we have, again, just a logical assertion, and we can calculate with it. And I will show you nice calculations, and this is what I call a contract, Bertrand. It's not a contract at the level of a program. It's a contract at the level of a system architecture, consisting in principle also of chunks of programs, but I call them component very much in the sense like Szyperski uses that term. Now let's play around a little bit. I think we have enough time to do that. Now let's talk about layered architectures. An interesting thing is, take your textbooks out and read the stuff about layered architecture. And most of it is bullshit, because they don't explain what a layered architecture is correctly. They say layered architecture is that you only have calls from above to below. Bullshit. Layered architecture is a design principle. And the design principle says, this is a layer of a layered architecture. The design principle says you have a service which is offered to the layer, and the service says is offered by the layer. And if you look at what this assumption is, that a service is offered, well, it's an assumption. So we can write it like an assumption. So we can use the assumption commitment idea. Now let's take two layers. If we compose them, keep in mind composition, maybe I should say that again. Here we have the specification of the layer under the assumption A. Provided service, we offer a service. And now we can have two layers and we can compose them if these two services are the same. This is a classical idea of composition. You remember parallel composition with an AND. And now this results in a layered system. Now we have put one layer on top of the other. And now we have to calculate the specification of the composed system, which is simple. Because now we can drop A2 from this and we get A1 implies P. Which means under the assumption A1, we get the service P. So design of architecture now is calculation in logics. And we can form those architectures, and we can even now consider layers which have not exactly A2, but have a stronger assumption, B. And we have to make sure that B implies A2. And from this, we get a new layer, which just makes sure that the service that is needed is exactly the service that is provided by the layer we are using. And I will skip that slide because this gives you then the exact rules of a layered architecture. And it's clear, and I think we all agree, that in many cases, layered architecture is exactly what you have to use. And we are now in the process of helping the automotive industry to go into layered architectures. I'm not sure whether you have looked at the architecture of cars. We don't even have a name for the architecture which is there currently. It's a completely rucksack architecture. And they know that if they don't change it now, they will never change it because they will lose their business. And so they are going into those layered architecture currently. And now I've shown you a complete theoretical approach to architecture, which I claim is also very practical. So I will now talk about the asset of foundations, or the advantage of having a semantic theory, a scientific foundation. And just to say that, I'm not saying you should always write assertions. You could also write state machines, or you could write just verbal definitions. But you should have a theory which tells you on which you can trust if you put things together. So you have to have a foundational theory. And that brings us into an engineering discipline. And so look at the principles which I try to follow. Not formal methods, but formal foundation. Occam's razor, keep it everything simple as possible. I use one concept of interface both for describing the functionality of a system and for describing the composition of architecture. It has to be flexible and universal. System components are schedulable and deployable units. I have modularity. Do we have a definition of modularity? Here's my definition. I call a theory modular if from the specification of subsystems I can derive a specification of the composed systems. That's modularity. And that's the modularity that I showed you. And we have a strict property orientation. Everything is based on logic. And we can add real-time and probability, so we get functional quality properties. We can describe what some people call rich specifications, talking about probability, talking about real-time properties. And we can write architectures. Here's a simple example of an architecture. And now we can talk about what's going on if we compose two systems. This is just using the formulas I have shown you. But I can also, I showed you that before, talk about what's going on inside the architecture. And this is a formula which describes what's going on inside the architecture. So this brings me to the end. What have we got? We have got a complete logic-based theory of service-oriented architectures. of functional feature architectures, of platform-independent component architecture. I didn't show you that, but we're also working on platform-dependent architecture. It's a fully formula specification techniques of properties, of real-time, of probability. We can extend it to classes and instances, which I didn't show. It can be used as a basis for methodology. You can form a language from that. You can do a tool design. By the way, we have done a tool, an experimental tool, which is around. You can use it. You can download it from the web. And it can be applied also in a semi-formal or informal way. And it does what I consider as very, very important. It allows you to describe also the architecture of cyber-physical systems, where some parts are software and some parts are hardware. Thank you very much.
Thank you very much. Over there.
Could you explain the term functional quality properties a bit more?
Yes, I can explain that. If you look at we have done a lot of projects in software quality. And now we can talk about a long time about the different quality aspects. I just take a few. Reliability.
Yep.
Is that fine with you as a software quality aspect? Some people say reliability is a non-functional property. I say it's not. It's a functional property. Mm-hmm. If I use a car, then the reliability is for me part of the functionality of a car. Yeah. How do I measure reliability? Let's keep it simple. Mean time to failure. And so I ask the question, what is the probability until I get a failure that the car gets stuck? Yep. And this I can express in the interfaces. And so I can have functional quality properties.
Okay.
Okay?
Okay, yeah.
Thank you.
Thank you.
I have some questions. So if timing and dynamic probability and timing are on the way to functional quality properties, and if you look at cyber physical systems, as you did, so what are the next classically non-functional properties which are on the way to functional properties?
If you're interested, we have written not just one paper about that. There are real non-functional quality properties. A real non-functional quality property is, for instance, readability. Mm-hmm. Another real non-functional quality property is performance. And performance not meaning performance for the user, but performance in the sense of how do you make use with your system of the resources, storage, and so on. Mm-hmm. This would be a non-functional property.
Yeah. No reason to be sorry.
Okay.
Just a minute.
Talking about response times, for example. Mm-hmm. So we are, you have a performance and you have response times, and actually you can measure them, so they are functional quality properties, but on the other hand, you said now it is a non-functional one. I mean, I don't want to make a theoretical discussion out of it, if you call it functional or not.
Let's have a theoretical discussion about it. Time is an interesting thing. There are functional properties which are timing properties, which are just real specification properties. If you specify an airbag, yes, the airbag has to come out after 180 milliseconds. And if it doesn't come out, you can forget about it. So it's a real functional properties. There are also soft functional properties, which you can also specify, which are often related to probability. If you buy a smartphone, you say, if I use my phone, I would like to have that in 99% of the cases. If I switch it on, it takes less than 2 seconds until I can do a telephone call. This would be a mixture of timing and a probability property, which is a functional property. And now you ask about performance. Performance has two sides. Mm-hmm. The performance of how much resources a software takes, and the performance of how long it takes if you do some functionality with it. Yes. We have to separate that. Yes. And it's even worse. We are used to define functional behavior by saying, well, we know that there is a system behind it, and for the system we know there's a certain pulse, and the pulse brings in a certain time, so these systems behave according to the pulse, which is wrong, because if we want to specify systems, I want to specify the required time, which is completely independent of the pulse, and then related it to the pulse and implementation problem. Okay?
Okay.
Thank you.
Over there. So where's the closest microphone? Oh, already there.
So one challenge is, of course, to get the requirements or the specification right for the top level components, and then breaking it down to sub-specifications of your sub-components, right?
Yeah.
And also there's one tricky thing with assume commitment specifications, that you can have nasty circular dependencies, and there are many things that a naive developer or engineer could do wrong. So what do you suggest, or how do you think an engineer could or should be supported in this?
There's one thing which I didn't present. In addition to the logics I've shown you, we use a logic for causality. Every system is causal. So it can only respond to input. It cannot respond to input which comes later than the output. And so we add a particular logical formula to that, and having that, we can show that those circularities you are talking about can be dealt with. So we can talk about fixed points, because interaction has fixed points, so we can show all the properties using this additional property. And the other things, of course you are right. I'm not saying it makes the whole thing easier. A complicated architecture still is a complicated architecture. But here you have a logical framework in which you can talk about the architecture in a clear, well-defined way, and you know all the rules you can rely on in doing that. That's the idea.
Okay. Thank you very much. Oh, sorry.
The description of architecture that you gave here is very much function-oriented, but we have also other domains where the data and data complexity is the most important thing. The function is very easy, but all the complexity is within the data. How do you handle that in your models?
I didn't talk about data descriptions. Frankly speaking, I think data description is a solved problem. And of course, you can, if you look at the approach, of course, you can assume that you can send not just simple events or messages, but very complicated data. So it's not an issue. Then you go in a different style where you write down data models. But I really believe data models is what we can do.
Okay.
Okay.
Manfred, thank you very much.
Thank you.